Hello again everybody and welcome to another video for college algebra. In this video I will be introducing logarithms, which we will come to know more or less as logs. So we will be for sure using an abbreviation for logarithms as logs. First, I'm going to explain and go over how log and exponential equations are related. I will then be going over how to evaluate logs exactly. That means without a calculator. Then we will be solving exponential equations by rewriting, and we will be solving log equations by rewriting. And the reason I will be going over two different types of solving equations or equation solving here is because of this first little idea here. Let's get into it. So how are log and exponential equations related? Here we have an exponential equation. You can see we have a base, we have a power, and yes, there was a variable switch real quickly. I changed both m's to a's because what I call the a over here is the answer, and we can rewrite this exponential equation into a log equation if we just place the base, the a, and the power in the correct place. So over here in the exponential equation, I call this the answer, and over here in the log, I call it the argument. And that's the best I can do with these. Anyway, so how can you easily convert from exponential to logs? Well, if you see this, we have a base that has a power or exponent. The base will become the base of the log, so yes, you will have to be writing log. And one thing I want to point out here is that the base is kind of like an exponent, but it's written, we'll say downstairs, aka in the basement. It's got to be down a little bit. You can sort of see the log and the argument are on the same line. The base is written a little bit below that line. Kind of like how when you write an exponent over here on the exponential, the exponent is pushed up above the base. All right, so we have the base will become part of the log. There it is. The power is what the entire log will equal. And the only thing that we have left to deal with then is the a, the answer. The answer will become the argument of the log, aka the inside of the log, if you will. And then going backward from log to exponential form, you can find the base by looking at the log. The base will get the power that's the log is equal to, so that's where this comes from. And then the last thing we do here, the a will go on the other side of the equation. That will be the answer in this equation. The argument becomes the answer. So why would we want to do this? Rewriting from exponential to log form or from log to exponential form? Well, more immediately, since we are talking about exponential equations, that means the variable will be in the exponent. And if you look over here, if we rewrite the exponential equation where the variable would be in the power, boom, in the log form, the variable is now no longer in the power, and we can solve for it very easily. Very, very easily. And then a little bit later, since the variable will end up being in the log a little bit later, if we want to get the variable out of a log, we can rewrite this equation in exponential form. And now this answer over here is easily manipulated so that we can solve for a variable. Let's take a look at a couple properties on the next slide that will help us in evaluating logs. On this slide, I have some basic properties that we're going to be looking at for logs. Like one here, we have log base b of 1 equals 0. And say for this next one here, we have log base b of b to the p power equals p. So let me rewrite this in exponential form, this top one here, just so you can see what's happening. So we have log base b. So I know if I rewrite this in exponential form, I will have a base b. I will also remember, and you should remember too, that the log is always equal to the exponent. So this is the exponent here. The exponent is 0, and we will put that on the base. The last thing we need then, we've dealt with the base, we've dealt with the exponent, we will set this equal to the argument. And the argument here is 1. And look at that. B to the 0 power is in fact 1. Now, quick reminder, the bases for all logs and exponentials are positive and not equal to 1. So this being the case, we have this base would be a positive number and not equal to 1. So again, any positive number to the 0 power is 1. And this is going to be true no matter what the base is, again, as long as it's positive and not equal to 1. Let's take a look here at this other property. We have log base b of b to the p power equals p. So if I just rewrite this here, I'm going to do some color coding. So there's b to the p power, and there's p. We take the base of the log, in this case b. We raise it to the p power because we know the log is always equal to the exponent. So here we go. There's the exponent. And what does that equal? Well, that equals the argument that we had here, b to the p power. Hey, yeah, b to the p power sure is b to the p power. But what this is better worded saying is, if you have matching bases in the base of the log and in the argument of the log, then your answer is just the exponent of the base in the argument. There it is. Like, that's the answer right there. It's just p. Let's see how we can use these properties in practice on the next slide. So here we will use the properties of the last slide, at least for a couple examples, so you can see how they work and how we can evaluate logs exactly. And I will also give a slightly different explanation as to what these logs are telling you to do. Hopefully that second explanation will be much more beneficial for you. So very much like we worked with here in a previous video with the exponential equations and solving them by using like bases, we can use that to our advantage here. So if I say log base 9 of 3, or sorry, log base 3, and I rewrite 9 to have the same base as the log, that would be 3 squared. And we can use that property that says if the bases match in the log and the argument, the answer is just the exponent. So there's that. The previous slide also had a property that said the log of any base of 1 is just going to be 0. So again, we can play this game here. I have log base 4 of 16. And this is our first instance of having a fraction in a log. But I know 16 can be rewritten in base 4 because, I mean, it's 16 after all. You know that 4 squared is 16. But this is not in the denominator of a fraction, and this is. So if we try to get this number out of the denominator of a fraction, we need to make sure that the exponent is negative. Since these bases match, we can then just say the answer is the argument, the exponent in the argument, or the exponent on the inside. So let me go back and circle these answers here. For this next example, I'm going to try the other, and I think more beneficial explanation for how this works, where we don't have to rewrite the argument as a similar base. So here, log base 5 of square root of 5. Log base 5 of square root of 5 is asking what power of 5 do I need to get square root of 5? In other words, this asks what power of the base will give me the argument. So let's just go back here a few examples. I think this might even make more sense. Look at the first example in red. What power of 3 do you need to get 9? 2. 3 to the second power gives you 9. What power of 9.2 will give you 1? 0. What power of 4 will give you 1 over 16? Negative 2. What power of 5 will give you square root of 5? Well, hopefully you've been chanting my little phrase from one of my previous videos. Square root is half power is square root. So if we're looking for an exponent here to put on 5 to change it to square root of 5, it's got to be the half power. Okay, so next I'm going to jump over to this example, and we'll come back and do these because these are a little bit trickier. But for this example here, you see what power of, well, there's no base, will give me 1,000. So I'm going to highlight that there. There is no base listed for this log. And if there is no base listed for a log, the base is 10. So now we can ask, what power of 10 would give you 1,000? So we can think about that. 10 times 10 is 100. Times a third 10 would be 1,000. So we would need 3 10s being multiplied together, which means that exponent would be 3. So you can take a look down here at this next example. This is ln. That's not capital I-N. This is an L for natural log. Not natural iog. So ln. And again, you'll notice there's no base here. The base for a natural log is e. So right off the bat, you can see that there are matching bases. We have an e base for the natural log, and we have an e on the inside in our argument. So our answer here would just be 8. All right, next, I'm going to come back up here to this example. The log base 125 of 5. This one is a little bit tricky. What power do you need for 125 to get 5? It's going to be 1/3. I don't think we're going to run into many, if any, examples of something that works like this. outside of a square root. So like this next one will be pretty important here. So what power of 121 would you need to get 1 over 11? One thing you always want to be looking for when you are evaluating logs exactly is square roots. So in this instance, I see that 121 and 11 are related because 11 is the square root of 121. So I know this is going to be equal to 1/2. But that's not it, because the 121, just like the 4 over here, the 4 was not in the bottom of a fraction, nor is this 121. But the square root of this 121 is in the opposite side of the fraction. And when you change sides of the fraction, you have to make your exponent negative. And I'm going to try to trick every last one of you out there with this one. What power of 3 do you need to give you 18? I'm going to make one of the most common mistakes here. Go ahead and think about it. What power of 3 gives me 18? It's 6, right? It's 6. It's not 6. It's not 6 because if you get your answer as being 6, all you did was divide 18 by 3. To tell you the truth, I don't know what exponent for 3 gives me 18. And if we were trying to evaluate this, we would just leave it. Like, that's it. I don't know what the answer is for that. I can use a calculator to approximate it. We'll learn about that a little bit later. So let's take a look then at how we can use evaluating logs and rewriting logs into exponentials and writing exponentials into logs from a couple slides ago to help solve exponential equations. So we have another way to solve exponential equations. We solve by rewriting as a log equation. So here we have this exponential equation, and I'm just going to do it like we did before. I know that 49 is 7 squared, so let me write this down. I've got 7x equals 1 over, here's what changed. I have 7 squared. I can rewrite this left side again. 7x equals, it can be rewritten as 7 to the negative 2 power because I want to move that into the opposite side of the fraction. So we have the like bases, and I can set those equal to each other and get that x equals negative 2. Cool, so we know what the answer is supposed to be. So how about we transform this or rewrite this into a log equation to see how it works a little bit differently. So in order to rewrite this in log equation, the base of the exponential piece, 7, will become the base of the logs. Let me circle that. There we go. That'll become 7. The exponent is what the log will equal, and the answer becomes the argument. So here we are. This is what we were just doing on the last slide. We can figure out what power of 7 do we need to get 1 over 49. Well, I went from a whole number to a fraction, so I know it has to be a negative. And 7 squared will give me the 49, so this should be 2. So x equals negative 2. So it's really good, and it's a valid way to solve exponential equations, But this method is much more useful if you can't make similar bases. And when that happens, we will end up with answers that are a lot like the last example on the last slide, where we couldn't simplify it down. It was just log base 3 of 18. So I think at this point, the easiest way to explain this would be to move on to the examples. So here with the first example, you see that we will not be able to easily convert 7 into some power of 3. We can't make like bases here. So what we can do instead is we can rewrite this in log form. So I will have a base of 3. Oh yeah, you have to actually write a log to convert an exponential equation into a log form. So there I have a base of 3. So the bases will match. Here the exponent is what the log will equal. And then the answer will become the argument. And that's it. We were able to successfully get the exponent, or the variable, out of the exponent. And yeah, like that's it. We have to rewrite it in log form and then solve for x. Like not that bad. X is already solved for. So this is it. Log base 3 of 7. And as of right now, that's going to be your answer. We will go over a little bit later how you can estimate these answers. But for right now, we just leave it in its exact form. So again, example 2, we have an exponential piece equal to the other side. I don't know what power of 5 gives me 91. Not a clue. I was pausing there to think, and I can't think of what power of 5 would give me 91. So since we cannot easily make like bases, what we will do then is rewrite this in exponential form. Log form, which again requires us to have a log. So make sure you're actually writing down the word log. The base here is 5. The next one, the exponent, that's what the log will equal. And the last thing here is the 91. The answer will become the argument. So here we have this new equation. The only difference between this one and this one is that x is not already isolated. So we have to come back through and subtract 1 and subtract 1, and we can write log base 5 of 91 minus 1 equals 3x. And this is where I love math, and math gets super confusing. There are no parentheses around this 91, but from your conversion, you can tell that this 91 is the argument of this log. This plus 1, when we subtracted 1 to get it away, this minus 1, is not going to be combined with the 91. And that is because the log will only have the first term as its argument. If there are no parentheses, the log will only have the first term for its argument. This term is not in the argument of the log. It's kind of like when you have this from the quadratic formula we did a while back, plus or minus 2 square root of whatever, 3, there we go, where you could not combine these 2's. You couldn't say this was 4 square root of 3. So that is very, very similar to what's happening here. You cannot combine this with the 91. So good luck with that, everybody. The last step here is to divide by 3, and we would just divide this entire side by 3, leaving you with log base 5 of 91 minus 1 all over 3 equals x. And there is your exact answer. So if I had to write some steps down for solving exponential equations with like bases are not possible, I would have these steps here. First step, isolate the exponential term if necessary. And you'll know it's the exponential term because you'll see an exponent with a variable in it. 2, rewrite the equation in log form. That was where we started with both of these. The exponential term in each equation was already isolated. So we could jump right into step 2 in that we rewrote it in log form. And then step 3 is solve for the variable if necessary. So here, x was already isolated, so that became our answer. Here, we had 3x plus 1, so we had to subtract 1 and then divide by 3 to solve for x. So here it was necessary to solve for x. Let's take a look at one more example. So here we have this equation. We're going to solve this equation, e to the x plus 5 power minus 14 equals 86. Here is the exponential term in the red box. We have to isolate that before we can do anything else. So yeah, we have to add 14 to both sides. And that will give us, what is that? E to the x plus 5 power equals 100. Nice. From here, now that we have isolated the exponential term, we can rewrite it in log form. So writing in log form again, we have to write the word log. The base is e. The exponent is x plus 5. That will always be what the log is equal to. And lastly, the answer becomes the argument. Now this one is a little bit odd because this log base e is exactly the same as natural log. The ln I mentioned earlier. And yes, I realize I used this notation, ln has base e, and that's still true, but we will not be writing that base e when we use ln. ln, we already know, tells us that the base is e. So our equation then changes to natural log of 100 equals x plus 5. If we want to solve for x, then we can subtract 5 and subtract 5, but again, remember, this minus 5 is not in the argument of the log, it's just 100, so you have to fight all instincts to want to combine the 100 and the 5, and it looks real funky. But you have to pretend like there are parentheses around this 100 protecting it from the minus 5, the negative 5 there. Again, the parentheses are not written there, but you sure can picture them in your mind. And now we move on to solving log equations by rewriting. And this is not the only type of log equation we will solve. We will take a look at those in another video. But for this video, the log equations, we will solve the log equations by rewriting the equation into an exponential form. And we will know to do this because not all terms are logs. So this is going to feel very similar to the last process. We have to isolate the log because we're starting with a log equation this time. Then we have to rewrite, just like we did in the last. Step 2 was rewrite. Step 3 was solve for x and simplify the answer. Well, we couldn't really simplify those logs in the last problems, but we will be able to simplify the answer in these examples. But here's the big one. You have to check your answer. This step will make more sense later. For now, we just go on the basis that logs cannot have negative arguments. Let's look at some examples. On this slide, you can see there are 3 examples, and normally when I put 3 examples on one slide, they're pretty short examples. So let's take a look at example 1. We have to isolate the log. Yep, there are no other terms with this log here. Now we can rewrite it in exponential form. So the base of the log will be the base of the exponential form. The log is always equal to the exponent, so 4 to the 1/2, and the argument becomes the answer. There we go. So clearly here, x will equal 2. Not bad. All right, for the next example. Wait, what's that? How does 4 become 1/2? Well, I'm so glad you asked. I get to chant it again in this video. Half power means square root. Square root means half power. Half power means square root. So whenever you see a 1/2 exponent, you're just taking the square root of the base. The square root of 4 is 2. Thank you for asking. Example 2. Log base x of 16 equals 2. So we have to isolate the log. Yep, it's already done. There are no other terms on the left side of this equation with the log. Next, we can rewrite in exponential form. So here we go. The base will get the exponent 2, and that will equal the argument. Okay, cool, yeah, x squared equals 16. We can just take the square root of both sides. We can put a plus or minus here, and we can get x equals plus or minus 4. But remember, I've been saying this in the last video and in this video, the bases have to be positive numbers as long as it's not equal to 1. So we cannot include the -4 here. We can only conclude that our base is 4 and not -4. The last example here, your first example with a log that has 2 terms inside. So remember this from a couple slides ago. It was something like natural log of 100 minus 5. And you can't combine these because you have to think that there are parentheses around the log. And when a log only has 1 term, we don't use parentheses on it. As you can see here, there were no parentheses around the x or the 16. But if we want more than 1 term to be in the argument, we have to use parentheses. That is your clue to let you know that the -4 is in the log. Whereas something like this, log base 42 of 5x minus 4, 5x would be the only term in the argument. Yeah, it gets, the notation is really amazing for logs. All right, let's get to it. So, again, also, terms are separated by plus and minus signs as long as they're not in grouping symbols. So yes, the argument has 2 terms, but this log is already isolated. There are no extra terms outside of this set of parentheses with the log. So we can go right into exponential form. Here we go. We've got 42. That's the base. We know the log always equals the exponent. In this case is 0, and that will equal the entire argument, 5x minus 4. So 42 to the 0 power is 1. 5x minus 4. We can add 4 together. or add 4 on both sides and get 5x equals 5. And then lastly divide by 5 and figure out that x equals 1. Now, I want to make sure all of these answers are correct, right? We have to check our answers. If I put 2 in here, for example 1, all I have to check then is to make sure that the entire argument is a positive number. It cannot even be equal to 0. It has to be a positive number. So if I put 2 in here for this x, will this entire argument be positive? Yeah, it's going to be 2. For this example, it was a little bit of a check, a little bit of a weird check. We already did our check when the variable is in the base. We just can't have a negative base. So this answer we know is correct. All right, last one here. If I take 1 and substitute it into this argument, I will have 5 times 1 is 5. 5 minus 4 is a positive 1, so the entire argument is positive. This answer is good. Let's take a look at a couple more examples. 2 more examples and you can be on your way. Here we go. We have example 4 being 3 times log of 4x plus 22 equals 6. All right, so the log in this term, yes, the log term is isolated, but we cannot rewrite if the log has a coefficient. So here we will divide both sides by 3 so that we can reduce these 3's and get log of 4x plus 22, and yes, these parentheses are necessary, equal to 2. I want to rewrite this in exponential form, but I don't see a base here. Oh yeah, I said it earlier. If you have a log with no base, an log log with no base, the base is 10. So now we can rewrite it in exponential form, no problem. The base is 10. The exponent is what the log is always equal to, and that will equal the argument. In this case is 4x plus 22. All right. So we know this will be 100 equals 4x plus 22. You can subtract 22 from both sides. You can divide both sides by 4. And 4 does not divide evenly into 78. So this would be 78 over 4, but this can be simplified. And so you should simplify it. And it does in fact simplify down to 39 over 2 if you divide the top and bottom both by 2. All right, so really quickly, if I take this number, 39 over 2, which is equal to, it's exactly 19.5, and if I multiply it times 4, that'll give me a really big positive number. What is that? 19.5 times 4 is 78. And if I add 22, I get 100. So if I substitute this number in here, I will have a positive number inside the log. So we want that. That is a good answer. Last, but certainly not least, here we have log base 6 of x squared minus 5x plus 6 equals 8. And I can tell you right now, I see something quadratic, I am probably going to have to factor. So let's get to a point to where we can factor, because I think that'll be a lot more pleasant than dealing with this log equation. So let's get rid of this log somehow. Oh, we have an extra term. You see how this extra term looks? It is a term that is not in the argument of the log. Yeah, we got to take care of that first. So let's subtract 6. Sorry, that reduces to 0. Okay, so now we can start rewriting. This would be log base 6 of x squared minus 5x equaling 2. So from there, we can rewrite in exponential form. So we will have a base of 6. I will have an exponent of 2 because the log is always equal to the exponent. And that will equal the argument of x squared minus 5x. So all in one step, I'm going to go ahead and say that 6 squared is 36, and I will subtract 36 from both sides. So on the left side of this equation, I will have 0 equals x squared minus 5x minus 36. I will hit my factor button and get x minus 9, x plus 4. There we go. And from there, I will set each factor equal to 0 and solve for x and get x equals 9 and x equals negative 4. Now we have to check both answers. So let me take a look here with the 9 first. If I substitute 9 into this expression, just the argument, I'm only looking at the argument, 9 squared is 81, and 5 times 9 is 45. If I subtract those, 81 minus 45, I will definitely get a positive number. And that is all we are after. So the argument is positive if I substitute 9 in for x. What about negative 4? This negative 4, you might just be looking at it and say, oh, it's negative, throw it out. Well, hang on a minute. It's not whether or not the answer is negative. It's whether the argument is negative. This whole thing after we substitute that number in to check. So let me see how that works. If I substitute negative 4 in here for x and square it, negative 4 times negative 4 is a positive 16. So that's a positive 16 when we square it here. A negative 5 times a negative 4 is a positive 20. So we would have had 16 plus 20. 16 plus 20 is 36. That's a positive number. This is a good answer. So I hope this last answer here shows you that it is okay to have negative answers as long as when you substitute it into the argument, the entire argument becomes a positive number. And that's it. That was the last example for this video. This video did in fact cover a little bit of assignment 19 in it as well, so if it seemed a little bit long, you did get some extra material in here. Yeah, I hope it was understandable. Good luck.